Yeah, thank you very much. And good morning, everybody. It's 11 p.m. here, so forgive me if I'm a little bit sleepy. So we're going to talk about software-defined radio. And software-defined radio is a fairly new technology, but it's hit the mainstream now. It started off as a few blokes tinkering away with circuit boards and working away in the wee small hours on software to go with it, and a huge amount of work was done. And now it's hit the mainstream, and the big three radio manufacturers are making software-defined radios, and it certainly seems to be the way the future is going to be. So, software-defined radio, what exactly is it? Well, I think most radio hams would have an appreciation of what software-defined radio is, or do they? There might be a few snags there. So I'm going to talk about that just briefly as a recap. DSP SDR evolution, how software-defined radio has been spawned from DSP technology. I'm going to talk about hybrid SDRs, like the new Yaesu radios. Some of the limits on direct sampling and why we have to go to the hybrid technology. A little bit on FFT and the panadapter, something on multiple receivers, and a little bit on software development. There's not as much software development going on now as there was. It was very dynamic probably 10 years ago, and there was new technology coming out all the time, and that seems to have slowed down a bit now. So the RSGB asked me for the talk to be technical, and I wasn't quite sure where to pitch it. So hopefully it's not too technical. There's no maths, well, not very much, and there's no software code, and I didn't include any vector diagrams, so we'll push on. What exactly is it? Most people know what a software-defined radio is, and many of us already own one. It's the latest transceiver from Alicraft, Yaesu, or ICOM, or Tentec. Of course it is. It's a flex radio or an Apache Labs Anon transceiver. It's an RTL dongle or a FunCube dongle. It's a Hermes Light, a SoftRock, or a Raspberry Pi Hat circuit board. These radios are all completely different, but they all claim to be software-defined radios. So what exactly is a software-defined radio? The SoftRock is a tiny quadrature sampling detector board. Is it the latest? Is it the same as the latest Alicraft transceiver, the new K4 that's coming out? Well, so we'll go into that. So SDRs are part of the digital revolution. You might be hanging on to your old LP records, but the world has gone digital. Your phone, your camera, TV, amateur radio, transceiver, they all went digital years ago, and so did music formats and things like that. And the main reason, there's lots of reasons, but the main reason is that digital stages don't add noise. So you can regenerate a noisy digital signal into a clean digital signal, and you end up with a nice clean system. With an analog, any analog transmission system, every time you amplify it or send it across the airwaves and receive it at another site, there's noise added, and you can't get rid of that noise easily. So whereas the digital signal, as long as you can tell what's a 1 and what isn't, and what's a 0, you can reconstruct the digital signal and have a completely noise-free result. And that's why telephone systems initially went digital, and everything else has pretty much followed on from there. So SDRs are a logical extension of the digital signal processing, DSP process. And the main aim of software-defined radio is converting the signals, the received signals, to digital as close as possible to the antenna. So DSP started off with AF and then went to IF, and so you could say that a software-defined radio is an RF DSP process. And the reverse is true also on the transmitter. The primary aim of an SDR transmitter is to convert the outgoing signals from the digital signal to an analog signal as late as you possibly can in the transmitter chain. So when I said that the digital signals don't add noise, when you convert an analog signal to a digital signal using an analog to digital converter, you do get some noise. It's called quantization noise, and it's due to the error between levels in the ADC. So if you had an 8-bit ADC, it would have 256 levels that can be described by those 8 bits. And if you had a level that was partway between that, between say 0001 and 0010, you would make a small mistake there, and that ends up averaging out as a noise signal. But it's very small, and with a 16-bit or 14-bit ADC, it's fairly negligible. And there are ways around it. They use randomization in the chips and oversampling, multiple sampling of the same data to average that out. So SDR receivers, they sound clean. When you first get one, you think, oh, well, this sounds a lot better. It sounds a lot better than my old superhet radio. And the main reason for that is because the frequency down conversion from RF to audio is not adding any noise. So you don't get noise in the mixers or the IM amplifiers and things like that. So what is the definition of a software-defined radio? Well, the ITU definition is not really adequate. In fact, in my opinion, it describes any radio with any kind of computer control, including CAT. What does it say? It says, a software-defined radio is a radio transmitter and or receiver employing a technology that allows the RF operating parameters, including but not limited to the frequency range, the modulation type, or the output power to be set or altered by software. And that certainly fits a CAT or ICOM CIV type scenario. For instance, the FT847 here, that has CAT control, but it's not considered to be a software-defined radio, even though it technically meets the ITU definition. So we can't use that. The FCC manages the radio spectrum in the US, and it's primarily interested in devices that emit signals on radio frequency. So their definition says that software-defined radios must always include a transmitter. There's no FCC definition for a software-defined radio receiver at all. Their definition says a software-defined radio is a radio that includes a transmitter in which the operating parameters of frequency range, modulation type, maximum output power, either radiated or conducted, or the circumstances under which the transmitter operates in accordance with the Commission rules can be altered by making a change in software without making any changes to the hardware components that affect the radio frequency emissions. So they're saying that has to be a transmitter. And again, they're saying that as long as you can change some of those things in software without actually affecting the hardware, then it's an SDR. Clearly, that's not what we describe as being an SDR. For instance, the FT 1000 MP, it's got IFDSP, but it's not field upgradable. You can't download a new firmware to it. It has to be done by taking the firmware chips out of the radio. So it's not considered to be an SDR. I like this definition that I found on Wikipedia a while back. It says software-defined radio is a radio communication system where components that have been typically implemented in hardware, such as mixers, filters, amplifiers, modulators, demodulators, and detectors, are instead implemented by means of software on a personal computer or in an embedded system. Now that pretty much describes what we would consider to be a software-defined radio. On the right there, we've got the Flex 6600M. It's direct sampling, direct digital sampling radio, and that SDR stage is followed with a fairly conventional Texas DSP stage. So that can be upgraded by loading new firmware from the internet or another source into the radio, and that can upgrade the features of the radio. And so that is considered to be a software-defined radio. This is an earlier Flex radio, the Flex 1500. It's got a quadrature sampling detector architecture. And all the modulation, filtering, demodulation, and stuff like that is all done by the PC software. So that clearly can be upgraded by changing the PC software. So it is also considered to be a software-defined radio. Okay, DSP evolution. So this is a typical double conversion super heterodyne receiver. Let's make a blob. So you've got an RF filter, RF amplifier, another filter after the amplifier, a mixer, and an oscillator that produces an IF output. There's a filter there to make sure that you only get the plus or minus output from the mixer, because you don't want the others, because you get images. Then there's an IF amplifier, then there's a second mixer, second local oscillator, fairly straightforward, and then there's IF amplifier, and eventually you get a demodulator and you get audio out of the receiver. So that's pretty much the standard receiver that we were using up until the time that DSP came along. This is a receiver with audio frequency DSP. It wasn't around for very long, really. And the main change is this area down here, where after the demodulator, there's an analog to digital converter. There's some digital signaling processing, which typically added sharp filtering and noise blanking and noise filters. And then there's a digital to analog converter to convert it back into audio, and you get an audio output. So this is the first time we see an A to D conversion inside a ham radio receiver. So it's the thin edge of the wedge. You've already started getting digital at this stage. So a little bit about DSP. Once a signal's been sampled and turned into a series of numbers, it can be manipulated to perform the functions that were previously carried out in the radio hardware. That includes all those filters and modulating and demodulating and things like that. Some of the code's actually quite simple. Now, for example, a volume control just adds a value to the numbers in the data stream. Here's an analog volume control. You've got audio coming in, you've got a pot, and you've got audio coming out. This is a digital volume control over on the right. You've got a data stream of 16 bits at about 48,000 bits per second, because that's a standard audio stream. And you have a number up here which you've assigned with software to be volume, and it might say, it might be 1 if the volume's low. So all that does is, in this box here, there's a piece of software that adds 1 to each of the numbers coming through, each of the 16-bit numbers coming through there. So these numbers here are higher by 1, which makes them a little bit louder. If the volume control was set to 10, they'd be a bit more louder when they get converted back to analog. So it's very, very simple. And a lot of the filters and things are actually remarkably simple when you actually look at the software. For instance, if the computer's looking at this stream of data and suddenly the numbers jump up to a higher level for a short time, that could be a noise spike. So the software can go, I don't want the noise spike, and it can just eliminate it and take it out completely. A noise filter, for instance, looks at the average speech level, which is considered to be a long time constant, and it eliminates or attenuates the signals that are above the average level but have a short time constant, such as a noise pulse. That's why your noise filters in a DSP radio or a software-defined radio, they don't work on noise that's below the average level, below the average speech level. Okay, we'll go to the next slide. Thank you. So software-defined radio takes the DSP further by always performing the demodulation on the digital signal and also providing providing the traditional band scope and filters and noise reduction. So software-defined radio is a merging of radio technology and computer technology. Some of the radio is still hardware, but the operating panel and the DSP is all software or firmware running on a CPU or a DSP chip or an FPGA, or in some cases on a personal computer. So there's three broad classes of software-defined radio receiver. This is the first one that came out. This is basically the Talo detector, and it's called a quadrature sampling detector. Let me draw a box. So it consists of two bits. This bit here is in hardware, and it's a very simple piece of hardware. Talo detector's only got 4 chips in it, and they're very cheap chips. And so that bit is hardware. You've got a filter, you've got an RF amplifier. The the RF signal is split into 2 streams, and a 90-degree phase shift is applied to one of the streams, which gives you the Q signal, and the other signal is not shifted, so it becomes the I signal. And then thank you. Inside the PC, you have 2 analog to digital converters. That's the sound card of your PC. People don't think of the sound card of the PC as being a analog to digital converter, but that's precisely what it is. And then all the DSP and demodulation, stuff like that, is done in the PC sound card, and that also converts the audio back to the D to A converter back into an audio stream for your speakers. So the second type of software-defined radio receiver is this. It's a direct sampling or direct down conversion, SDR. It's got the same RF filter, the same RF amplifier. It's got an anti-alias filter, which stops the analog to digital converter sampling data that you don't want it to. And instead of an oscillator, these are clocks, so it's a square wave instead of a sine wave. And then there's a FPGA, and that slows the data down to a speed that can be sent to the computer. And the output of that is 2 streams, whereas the previous one, the streams were at audio, and then they were converted to analog. They were converted to digital by the PC. This type of radio puts out 2 digital streams that are at 90 degrees to each other. And they're carried via Ethernet or USB to the DSP stage, which is running on software on your computer, or it might be running on software or firmware in your radio, such as your ICOM radios, where it goes through to a Texas DSP chip, and then eventually to audio. So This kind of receiver can have the DSP performed in the computer, like the Apache Labs Anon radios or the Sun SDR radios or the Flex radios, or it could be in the radio itself, like the ICOM 7300 or ICOM 7610. Or a third option is the PC could be in the radio, like the Expert MB1 or the Apache Labs Andromeda radios. So they're more like the first version, where DSP is being done on PC software, but the PC is actually residing inside the radio box. So that's a different hybrid type. The third kind is a hybrid SDR. This uses a standard super heterodyne stage at the start and mixes the signals, the RF signals, down to a frequency that the ADC can sample. And then from there on, it's pretty much like a direct sampling radio. So this bit's super heterodyne, and this bit is the SDR. They're used mostly in VHF and UHF radios because you can't get ADCs that will sample fast enough to sample up past about 160 odd megahertz. After that, you need to be able to reduce the frequency down, and typically you reduce it down quite a lot. In the Yaesu radios, for example, it's mixed down to 36 kilohertz. So the SDR ADC doesn't have to be particularly special at all. So the direct sampling radio is as close as we can get to the antenna, but we have to back up a step if we want to go to high frequencies, and that's where this hybrid SDR with a super het front end followed by an SDR back end takes over. So IF-DSP moved the digital sampling to the IF. IF-DSP had the digital sampling at the audio frequencies. IF-DSP moved it closer to the antenna into the IF. Direct sampling moves it right to the antenna virtually, except for an RF amplifier and a filter. And it's fine for HF, but as soon as you want to go to VHF or UHF or micro frequencies, then you've got to go back a step and use some sort of super heterodyne stage. This is the, just for interest's sake, this is the block diagram of the two receivers in the Yaesu FTDX101. You've got a super heterodyne receiver here. This is the sub receiver down here. They're both exactly the same. And so there's an RF amplifier, there's a mixer with a local oscillator. You get an IF coming out of here, and it goes into an SDR block where there's an analog to digital converter, an FPGA, and then a standard Texas DSP block, a digital to analog converter, audio amplifier, and output to the speaker. And in addition to that, actually, I'm getting ahead of myself. So we fade that out. There is actually an SDR in the Yaesu radio, and it's here. So there's a takeoff at the end of the RF amplifier, and it goes into an analog to digital converter into the FPGA and straight into the display. So this is a direct sampling SDR, but it's only used for the band scope. So if we take that out, then you get the super heterodyne hybrid technology where you've got a super het stage here and an SDR stage and a DSP stage. Just for interest, this is the the simplified block diagram of a Yaesu FTDX 5000, which is not an SDR. And you see that you've got the same IF and mixer and a local oscillator to produce an IF here. And then there's a second mixer and local oscillator to mix from the 9 megahertz IF down to 24 kilohertz for the DSP. So it's not significantly different really to the FTDX 101. That's the FTDX 101, and that's the FTDX 5000. That's not an SDR, and apparently that is an SDR. So I'll leave that up to you to work out, because I find that a little bit confusing. Yeah, direct sampling limits. This is Harry Nyquist. He's the father of digital sampling. Without his contribution to science, we might not have the digital systems that we have. He was born in Sweden, but he studied in America in North Dakota, and eventually received a PhD in physics from Yale in 1917. Now, the reason this guy is so important is that he is the guy that worked out that your ADC sampling rate has to be at least twice the highest frequency of the bandwidth the signal's being sampled. So, and that is so that you can recover the analog signal back after you've messed around with it with your digital signal processing. If you don't sample that at least twice the highest frequency, you cannot recover or cannot accurately recover the original signal. So if you want to sample all of the HF band in the 6 meter band up to 54 megahertz, that means you have to have an ADC that can sample at least 108 mega samples per second. So it's 108 million 16-bit samples per second are coming out of that ADC. So you need quite a lot of computer processing power to manage that. Or you can use a hybrid technology, and you can shift the frequency down using a superhet stage to say 36 kilohertz. Now, at 36 kilohertz, you've only got to sample it twice that, which is 72 kilohertz. So that's a heck of a lot easier, much, much cheaper analog to digital converters if you use a hybrid technology, which is probably why that's the way things are going. This rule is also why sound cards, sound card in your PC, you'll find that it's either working at 48 kilobits per second, which gives you 24 kilohertz audio, which is hi-fi audio, because you can hear from roughly 15 hertz up to about 20 kilohertz-ish. So 48 kilobits carries that quite nicely. Or your sound card is also able to do CD audio standard, which is 44.1 kilobits. And that is 22.05 kilohertz of audio. So, yeah, we've got a lot to thank Mr. Nyquist for. So direct sampling is limited by the range of the frequencies that the ADC can sample on each Nyquist zone. An ADC can actually sample frequencies higher than the Nyquist zone, and you can use them, but you can't use, and that's called a second or third Nyquist zone. You can use them, but you can't use them at the same time as you use the signals from the other Nyquist zones. Does that make sense? No. So you can't use two Nyquist zones at once. For example, the Sun SDR Pro transceiver can cover from 0.1 to 65 megahertz, or it can undersample and it can cover from 95 to 155 megahertz. So this transceiver can cover the HF bands, including 6 meters, and the 2 meter band, but it can't cover the 2 meter band and the HF bands at the same time. You have to choose one or the other. This ELAD receiver has a maximum sample rate of 122.8 megahertz, or 128 million samples per second. So it can cover frequencies from 9 kilohertz up to 108 megahertz in 2 ranges using undersampling above 54 megahertz. This radio can display up to 24 megahertz of bandwidth at the same time on your panadapter, which is pretty wide. Now, I note that they don't call this radio an SDR, they call it a direct sampling wideband receiver. And I think that's because of the confusion about what exactly an SDR is. So any SDR radio that's capable of operating in the VHF or UHF range will be a hybrid. And that limits the bandwidth that the radio can cover. Most of them are about 10 megahertz. Some of them are a little bit wider, like that ELAD. The problem with this is the way that we use the VHF, UHF, and microwave spectrum is different to the way we operate on HF. On HF, we tune across the bands. On VHF and UHF, the activity is based around fixed channels generally. Even when it isn't like an EME and satellite operation, it's restricted to small bands with wide spaces between them. And that doesn't really suit SDRs, because we've got an SDR that can display 10 megahertz. It might only be able to display a couple of local repeaters with a whole lot of unused spectrum in between. Now, you can scan the bands or program memory channels, but then you might miss something because you really want to be able to see all of the signals all of the time. So what we need is radios that can receive multiple channels at the same time. For example, all of your local 2 meter, 70 centimeter, and 6 meter repeaters at once, or 3 or 4 airband channels, or all of the marine band channels. You can't currently do that. So this is easier to achieve with radios that are harnessing the power of a PC rather than radios with knobs like the IC 9700, which has 2 receivers. For example, the SDR Play receiver, using the SDR Uno free software, they can create 16 receivers. So you can monitor 16 channels at UHF or VHF at the same time, as long as they're within a certain bandwidth. So there is still an argument for black box SDRs that plug into the PC. So SDR developments, well, it was very exciting in the early days. There was a lot of development, and most of the software was open source software, so a lot of people tinkered with it, and there were a lot of software forks and changes going on, and new ways of doing DSP, and new radio coming out pretty regularly. Every 2 or 3 months a new radio to come out. It was all very exciting. And a lot of people spent thousands and thousands of hours developing new SDR hardware, and particularly software. And the software, they gave it all away for free. It was all pretty much open source. And there was great collaboration, and that really drove things forward. On the other side, there's commercial interest in military software-defined radio. Most cell sites are software-defined. A lot of military radios are software-defined. So there was a lot of development going on there outside of the ham radio world as well. So there was lots and lots of receivers particularly, and transceivers, but mostly receivers. Receivers because they're easier to make, and the big benefits that you get from software-defined radio affect receiver performance. You can make a software-defined transmitter and it's fine, but it's no better generally than a conventional one, whereas there were huge advantages in making receiver software-defined. It all became so popular, the SDRs become a bit of a buzzword, and everybody says their radio is a software-defined radio these days. and not all of them are, and some of them are hardly software defined at all. Another development that's come out is GNU radio, or GNU radio. This has allowed people to develop their own software-defined radio software using code blocks. It's kind of a Lego system, and it's really good because you don't have to reinvent the wheel. You don't have to write your own panadapter software. You don't have to write your own digital DSP software. You can just use blocks that other people have written, and you can tinker with them, and you can plug them together, and you get a software-defined radio code out the end. And that's great, but I wonder if it stifles innovation a little bit, because people aren't driving the code further. They're just reusing the code blocks other people have developed in Python or C++. So there hasn't been really anything much new over the last few years, which is a bit of a disappointment. Apart from the big three, the ICOMs, of course, have revolutionized the transceivers and probably killed a lot of the used radio market, because they've released radios, ICOM and now Yaesu, have released radios that have just offered a lot of features that we used to be only on the very high-end radios, and they've offered these features like PSK decoders and RTTY decoders and band scopes and sharp filtering and all this sort of stuff at a reasonable price that a lot more people can afford. And so it's really revolutionized the ham radio, and there's an awful lot of IC 7300s out there. I did a talk to a ham radio club in America, and they said that 86% of the membership owned an IC 7300, so remarkable. So why are the big radio manufacturers now waking up and making SDRs? Why have they changed? They had a great market, and they've been very successful for a long time. And so why did they change? The answer is better performance, better features, much cheaper to make, because RF circuitry is difficult to make, and difficult to make well, particularly filters and things like that. Good filters are expensive to make and difficult to tune. And because so much of it's in computer software, there's really no alignment required with these new radios. So it makes the production line much easier. You have to speed up. So panadapter. Software-defined radio people call it a panadapter, and the older DSP radios call it a band scope. It's basically the same thing. A band scope, the VFO frequency sits in the middle, and you can see frequencies above and below. A panadapter, you can see a chunk of the band, and you can move the receiver or the transmitter around within that area. So you could transmit here and receive here, even though the center is here. So that's the main difference between a panadapter. Now, Yaesu and ICOM get around this, and they don't use either term. They don't call it a band scope, and they don't call it a panadapter either. They just call it a scope or a display. This is a picture of CUSDR, which unfortunately the development stalled on, which is a real shame because it was a lovely piece of software. People sometimes say, oh, well, you know, I can connect my my new ICOM radio or my new Yaesu radio to a monitor and it looks fab. And I go, ooh, I don't really think it does. When you're used to something like this, which is very high resolution, those other displays really don't cut it. And the other thing about this is that this type of display, you can control all the radio functions because all the radio functions are in the PC. Whereas the scope you display on a monitor with these other radios, you can click on it and move the frequencies and things, but that's all. Just one point. The hardware radios with knobs are still using S meters. The panadapters on software-defined radios tend to not use S meters. They tend to display in dBm, which is a much better thing because S meters really don't mean anything. S9 on one radio is not the same level as S9 on another radio, whereas a dBm is a dBm. This scale here on this is so accurate that you can use it. You can use the device as a spectrum analyzer. So time and frequency and range. So the ADC in an SDR converts the spectrum into digital signals that divide at a defined rate measured in millions of samples per second, typically 122.8 million samples per second for a direct sampling HF receiver. But for a hybrid receiver, it could be much, much lower. It could be something like 72 kilohertz. An ADC is working in the time domain because it's taking it's deciding what the level of the RF signal is at units of time. Now that's fine for the receiver because that's what we want. And we want the DSP to produce data that can eventually be converted back into analog. But for the spectrum display, we don't want that. We don't want to see what the level is at different times. We want to see what the level is at different frequencies, and that's called the frequency domain. And the fast Fourier transformation is a very complicated mathematical structure that converts data from the time domain in millions of samples per second into bins in the frequency domain. Each bin has a width, so it's the level of the signal within a small chunk of frequency. They say it might be 10 hertz wide. And the spectrum scope is actually made up of stacking all those 10 hertz wide bins side by side by side to produce an image of the frequencies across the spectrum. So the new radios offer two independent receivers. That's a big step forward with these SDRs. The older radios had dual watch, which was sort of two receivers in the same band. But these radios can have two, you can monitor two completely different bands at the same time. So you could monitor a band to see if your friend turns up for a SCAD while you're working another station on CW on a different band. Or you could decode CW with a skimmer on several bands at the same time. Or you can listen to the pile-up and the DX station to find a good spot to transmit on. Or you could just have one receiver sitting on a band, say the 6 meter band, just to see if it's open or not. You could sit it on a beacon frequency and just leave it sitting there. Great for contest stations because you can check what a band's like before you switch, and also you can tune around on one band while it's gone a bit quiet on the other band. Some SDR receivers offer as many as 8 completely different independent receivers. So in the hardware radios like the Yaesu and the ICOM, you get 2. This is a flex radio showing 4, and some of the flex radios can actually do 8 receivers. And I've only got 2 ears, you say. I can't listen to 2 things at the same time, or 4 things at the same time. Well, you don't have to listen to it, but you can see what the band activity is like on different bands. So in the middle here, you've got a split operation. So you're transmitting on one part of the band and receiving on a slightly different part of the band. And you're also monitoring the 20 meter band and the 10 meter band at the same time. Here we go for time. Ooh, I think we're just about up. I might have to skip this. So direct Fourier conversion is a technique proposed by Phil Harmon. Unfortunately, it's stalled, and the idea of it is that you do an FFT on the entire HF band and then just pick the bits you want. Unfortunately, it doesn't work as well as it should, and so there's some bugs to be ironed out of that. So although converting all of the FFT bins back into the time domain is feasible, converting selected FFT bins causes horrible problems that are yet to be resolved. So I'd really like someone to pick that up. Other advancements, controlled envelope SSB and dynamic pre-distortion. CESSB is used experimentally by some operators, and it is a feature of some radios. And it can give you a boost of average output power of about 2.5 dB. What it does is the software looks at the modulating audio and it modifies the data so that overshoots that would cause clipping are eliminated. And that means that you can push the average modulation level up. Now, a 2.5 dB increase in signal is like stacking a Yagi on top of your existing Yagi. So it's a huge improvement without having to add any extra hardware, so it's well worth doing. It could turn a 100-watt transmitter into effectively a 178-watt transmitter, and it can turn a 1,500-watt transmitter into a 2,600-watt transmitter. So that's one of the things that they're doing. Pre-distortion is the other thing. It's a way of cleaning up these intermodulation products that are inevitable on the sides of a wanted signal. With pre-distortion, the same sort of thing happens. You look at the output that the radio is putting out and you correct the modulation that's going into the transmitter so that you don't get the intermodulation products. Now that's fine, but it's not a fixed thing. It has to change continuously as the modulation changes, so it's quite clever and difficult to do. You can get a typical improvement of around about 20 dB of transmitted intermodulation performance. So there's a typical transceiver with a two-tone test, and this is the IMD that's produced out of that two-tone test. And here's the same transmitter running pure signal, and you can see just how much cleaner it is. It is truly amazing. So the ARRL guideline says that the largest intermodulation peak, which is that one there, should be at least 30 dB down below the PEP level, which is the top of the screen. With pure signal, this particular radio, which is my radio, my N100, is achieving 80 dB down below the PEP level. So that is amazing. Hooray, I've finished right on time, I think. So
thank you very much.
Back over to you, Rob.
Yeah, not got too many questions, but there's been quite a lot of discussion going on the chat. But you did say that early on that there's not much development going on now. This is what people want to talk about. Would you say we've reached peak SDR then, or what?
I hope not. I think originally there was a lot of people tinkering around with boards, and they were developing new things, and it was very exciting because there was a lot of new changes, and they were collaborating with a lot of other people, and they were making a lot of new changes, and so it was very dynamic and very exciting. And those easy fruit, or that easy advantages, there's not so many of them around now. So I don't think it has peaked, and I'd like to see things like the direct Fourier conversion and the dynamic pre-distortion and thing included in more radios. There's no reason why that couldn't be included in radios that have knobs. So yes, there's still advances to be made, but maybe not as quickly.
Okay, I'll just put a couple of points to you that came up on the chat. David Crump disagreed when you said it seemed to have stalled. He said lots of SDR developments for amateur TV use in the last 3 years. And John Regnault, hello John, says I also disagree. The use of GNU radio modules can be incredibly innovative in amateur radio, an extension of open source development. A few quick thoughts on that.
Yep. Okay, so as far as GNU radio goes, I have no experience with it, and I'm sure that it is right. My point really was that because you can just pick up modules and reuse them, maybe not so much innovation is happening, but maybe it is, and that would be great to see. And I'm sorry, what was the first one?
Digital TV.
Oh, yeah. Radio. Again, I have no experience with it. That's great. I think digital TV is a logical way to go. SDR is a logical way to go for digital TV, because digital TV requires a wideband signal, and SDR is excellent at wideband stuff. So yes, there's huge advantages in using SDR receivers for that, and for satellite use as well, things like your QO100 and things like that. I'm sure a lot of people wouldn't be on that satellite without SDRs.
So GB3RS has been on QO100 already today. Well, Andrew, time is getting on. It must be coming up to midnight with you. Well past your bedtime, I imagine.
It is past my bedtime, yeah.
Thank you very, very much for giving us the time today. If you'd like to find out more about Andrew's book called Software Defined Radio, funnily enough, it's available from the RSGB shop. Have a look at the website.